Hello everybody. So we're still talking about the multiple reactions, and in this case in this video we are going to discuss how we can express the multiple reactions in terms of equations for doing the calculations of the number of moles of the product in terms of the number of moles of the feed. Which we did before for single reaction, but there are going to be more details here. So what we have here is one important thing, that if we have more than one reaction, let's say these two reactions that we have here, and that for these two reactions the reactants are the same. It's ethylene and oxygen, but the first reaction it produces ethylene oxide, the second produces carbon dioxide and water. And now if you want to express the stoichiometric coefficient for any of the components, then the stoichiometric coefficient should be taking into account that this is the coefficient of this specific species, and that it is for the specific reaction. So these two information should be taken into account. That's why we have this sentence here that the coefficient of component I in reaction J is defined as nu Ij. So just to make things simpler, ethylene would be given the symbol E, ethylene oxide would be EO, carbon dioxide C, oxygen O, water W, and now we can list the stoichiometric coefficient. So the coefficient for ethylene in the first reaction is going to be nu E1. This is the coefficient of ethylene in the first reaction. And this is the ethylene in the second reaction, it's nu E2 is -1 as well. For oxygen it's going to be clearer. So oxygen in the first reaction, nu O1 is -0.5, nu O2 is -3. The same for ethylene oxide. We have only ethylene oxide in the first reaction, so it's going to be the nu of EO1 is 1. For carbon dioxide 2 is 2, for water 2 is 2. And of course there are some compounds that are not present in the some of the reactions. So for example, water in the first reaction is going to be 0. The coefficient of water in the first reaction is 0. Carbon dioxide in the first reaction is 0. Ethylene oxide in the second reaction is 0. So this is something that we need to keep in mind when we have more than one reaction, that the subscript of the coefficient should include the two information. Now let's see how we can deal with balance with systems that have multiple reactions. So what we will do here is that we will assume that the reaction will take place sequentially. It's not simultaneously, it's sequentially. Sequentially means that one of them starts and ends, and then the second reaction starts afterward. Let's assume that we have the two reaction, A plus 2B go to 2C, and 2A plus B go to D, and that we have the feed to the reactor is 100 moles of A and 200 moles of B. Now let's say that for the first reaction that 70 moles of A are consumed, they react with 140 moles of B, producing 140 moles of C, and then the product is 100 minus 70 is 30. 200 minus 140, this should be 40. This is a mistake, I'm sorry. This should be 60, I'm sorry. This should be 60. And then we have 140 moles of C. And then what we mentioned is that after this reaction ends, the next reaction starts. So again, this should be 60. We have the 30, 60, 140. Of course, 140 is not part of the second reaction. So we have the 30 and 60, and the 20 consumed for the first reaction, 10 in the second, 10 in the produced in the in D. And then we have the output is going to be 10. Of course, this is going to be 50, and this is 10. And now we can do the what we did before, that we can express the numbers in terms of the table, or we can express the numbers using the extent of reaction calculations. So with the extent of reaction, for the first reaction we can say that the number of moles of A in the product equals the number of moles of A in the feed, plus the coefficient of A in the first reaction multiplied by the extent of the first reaction. We know all the information except the extent of the first reaction. So here 30 is 100 plus negative 1, which is the coefficient here, multiplied by xi1, so we can calculate the extent of the first reaction. And the same for the second reaction. We have the number of moles out is 10 minus 30 equals 30 plus negative 2 multiplied by xi2, and xi2 equals 10. So this is something that we can do. But this is okay, and this is fine. We have no problem with this, assuming that the reactions are sequential. And if the reactions are sequential, then we know that there will be an intermediate value of A between the two, and of A and B, of course, between the two reactions. And in reality, we cannot jump into the reactor, inside the reactor, and count the number of moles of A that will happen in the first reaction, and then before the second reaction starts. Of course, this is even if this is possible, the reactions don't go this way. So the reactions don't start one by one. It's not a line that each one takes his surface and then followed by the next. They all happen at the same time. So the application of these equations here is not possible, because I don't know NA out 1 and NA in 2. I don't know this. So what we can do is we can write the equations and then see how we can simplify them. So we have these are the same equations that we had in the previous slide, these equations without substituting with numbers, and then we can add the balance equation. So I know this is the output of the first reaction, which is the input to the second reaction. So if we add the two equations, then we will have out 1 plus out 2 equals N1 plus N2 plus the new A1 xi1 plus new A2 xi2. And we know that the number here is the same number here. Again, this is 60, not 50, but we know that this number here is the same as this number here, which means that the NA out 1 equals NA in 2. So they will cancel out, and the equation will end up to be this. And this is a very, very, very nice equation, because it doesn't go into the intermediate values of A inside the reactor. We just calculate the product of the reactor, the number of moles of the product of the A from the reactor, in terms of the number of moles of A fed into the reactor. And then we have the coefficients and the extents of reaction. So this equation is similar to this and this. It only includes one more term here, which accounts for the consumption of A in one extra reaction. So in general, if you want to calculate the number of moles of product of a reactor, of a component from a reactor that contains multiple reactions, then we can use this equation here. It's Ni equals Ni node plus the new I1 for this component, whatever this component is, multiplied by xi1 plus new I2 xi2, new I3 xi3, and so on. So the general form of the equation is this, that it is Ni equals Ni node plus the multiplication of new Ij xij. So it applies to any number of equations or reactions that we have. So back to the example that we were looking at, the for the ethylene oxide converting to or ethylene converting to ethylene oxide or carbon dioxide and water. So if we want to calculate the number of moles of ethylene oxide, ethylene that is produced, it's going to be the number of moles of ethylene node, which is the feed, plus the coefficient in the first reaction, which is -1, multiplied by xi1, which is the extent of the first reaction. It's also present here, so it's going to be minus xi2. Same for oxygen, it's going to be number of moles of oxygen in or node minus half xi1 minus 3 xi2. This is 3. I don't know, I have a lot of mistakes here, but this is -3. I'm sorry for these mistakes. And for ethylene oxide, it's going to be the ethylene oxide in the feed plus xi1, because the coefficient here is +1. The same for carbon dioxide, it's +2, and water, it's the feed plus 2 xi2. So again, this takes us to the thing that we mentioned before, that if we know the extent of reaction, we can calculate a lot of things. And this is the same thing here. We can calculate a lot of things with the knowledge of the extent of reaction. Now there is a very important point that I want to make here, which I think I mentioned before quickly, but it's important to take a closer look at very closely here. That the general equation that we started in the first part, or the very first part of this chapter, that this is the general mass balance equation, and we said that under steady state conditions there is no accumulation, so the equation would be summation of input plus generation minus output minus consumption equals 0. And we said that the terms for output and generation and consumption, the generation and consumption represent the reactions. If we have moles generated due to reaction or moles consumed due to the reaction, these terms account for them. So if you look at this equation, you can rearrange it to be the sum of the output equals the input plus generation minus consumption. If you compare this equation to the equation that we just had or found after the derivation in the previous slide, you'd see that it's exactly the same. So the output is this, the input is this, and the generation and consumption are expressed by the terms of the extent of reactions multiplied by the coefficient. So this is what we are going to be, or one of the two methods that we are going to use to do the mass balance is this, that it is the general balance equation for reactive system. It's going to be the same as before for non-reactive systems with the difference of this term. And if you have no reactions, so the coefficients are all zeros and the extents are zeros, then the equation will go back to the previous shape, that the inlet equals the output, or in equals out. So it's the same thing. So this makes a lot of sense, and it's kind of, we are putting everything together now with all the information that we have been discussing since the reactive system part. This makes a lot of sense. So we will take one example quickly to apply what we discussed. If we have the two reactions, that ethane goes to ethylene and hydrogen, and ethane plus hydrogen go to methane, and they take a place in a continuous reactor at steady state, and we have a mixture that consists of 100 moles in the feed to the reactor. These 100 moles are 85% ethane, and the balance is inert. Inert is any material that it's not necessarily an inert gases like xenon or neon or helium. It's a gas that doesn't contribute, or a material that doesn't contribute to the reaction. It can be carbon dioxide, it can be anything, it can be nitrogen, but as long as it doesn't contribute to the reaction, we call it inert. So it's a very common word that we use in reactors. So the fractional conversion of ethane is 0.501, and the fractional yield of ethylene is 0.71, and we need to calculate the molar composition of the product gas and the selectivity of ethylene to methane production. So again, let's put the symbols, and then put a summary of the givens that we have. So the givens that we have first are going to be the coefficients. So I know that the ethylene in reaction 1 is -1, ethylene in reaction 2 is -1. This is ethane, I'm sorry. Hydrogen in reaction 1 is 1, ethane in reaction 1 is 1, hydrogen in reaction 2 is -1, and methane in reaction 2, I didn't put methane, but methane in reaction 2 should be +2. And we also have the flow rate of the mixture. 85% of the feed is ethane, so this is the number of moles of ethane in the feed. It's in E node is going to be 85 moles. And we know that the fractional conversion of ethane is 50.1%, and the yield of ethylene is 0.471. So these are the list of givens, and this is something I like to do actually, is to put all the information, all the given information in front of me, so I can see them all. I don't have to go back to the problem statement anymore. So yeah, let's go back just to see. We need to calculate the product gas molar compositions. So this is something we see a lot. So the easiest thing to start with is the conversion and yield. They are easy relations to to start with. At least we can just write the equations and then see what we will do. So for the conversion, it is, we said it's number of moles of E in the product minus number of moles of E in the in the feed minus product over the feed, which, and we said that the numerator is the amount consumed or reacted. So it is, if we simplify the equation, is going to be 1 minus number of moles in the product minus the feed number of moles. I know the feed is 85, and from this we can calculate the number of moles of E in the product. Now we know the number of moles of E in the product, and we know the number of moles of E in the feed. And we also can use the yield relation. The yield is the number of moles of ethane over the theoretical number of moles of ethane. Again, let's go back to the problem. The theoretical number of moles of ethylene to be produced is the same number of moles of ethane in the feed. So it's, if this is it's 85 moles, then this is going to be 85 moles. Again, the formula that I'm using here is the general formula. If you'd like to get it as 85, it's fine. It's not a big deal. So we can calculate from this the number of moles of ethylene that are actually produced. So now we have some extra information that we can use. So the equations that we can write are going to be the balance equations for the components that we have. So the balance equations are going to be the extent of reaction relations that relate the number of moles in the product with the number of moles in the feed. So let's start with the ones that we have information about. So this is for ethylene. So the number of mole ethylene in the product, ethylene is only present in the first reaction. It's not in the part of the second reaction. So for the generation and consumption, we will only have one term. So what we will have here, it is the number of ethylene in the feed plus the extent of reaction. We have no ethylene in the feed, so the extent of reaction is going to be 40, which is number of moles of ethylene. Now we can use the second information here for ethane. Ethane is present in the two reactions. It's -1 here and -1 here, which we have here. So we can write the equation, the number of moles of ethane in the product equals the number of moles of ethane in the feed minus Xy1 minus Xy2. I know the number of moles of ethane in the product, which is 42.4, and in the feed I know it is 85, and we know Xy1 is 40, so we can calculate Xy2, which is 2.6 moles. So now, since I know Xy1 and Xy2, I'm done with everything. I'm just using the equations to calculate the number of moles of hydrogen. Again, if we go for hydrogen, hydrogen is a product in the first reaction and a reactant in the second reaction. So it is -1 here and +1 here. And so we can calculate the number of moles of hydrogen. It's very straightforward. It's Xy1 minus Xy2, so it's 37.4. And the same for methane. It's only present as a product in the second reaction, so we can calculate the number of moles of methane. And then we can calculate the molar composition. We have now all the components, the number of moles of all the components, 1, 2, 3, 4. We have 4 components. Let's double check. We have ethylene, hydrogen, and methane. We have only 4 components. So now we can calculate the total number of moles, and from the total number of moles we can calculate, and we have 15 moles of inerts, by the way. I forgot them. So we have 5 components. So the total number of moles, if we, I don't know what is the value of the total, but if we divide each one of them by the total number of moles, we can get the mole fraction. And finally, we are asked to calculate the selectivity of ethylene to methane. And we said the selectivity is very straightforward. It's number of moles of ethylene to number of moles of methane. So it is going to be 40 divided by 5.2, which is 7.7 moles per moles, which is dimensionless. So this is a good example that we can see how we can apply the equations. In the next video, we'll start the actual mass balance calculations on the actual reactors, and we will see the approaches that we can use to do the mass balance. So I'll see you next video, inshallah. Goodbye.